Hello, I'm Norman Wildberger. Today we're going to have a look at more applications of row reduction, the fundamental algorithm in linear algebra. Last time we applied it to the three main specific problems in the subject. Today we're going to look at applications of row reduction to various issues relating to the geometry of three-dimensional and two-dimensional space. In particular, we're going to be looking at linear transformations and how row reduction helps us understand some interesting aspects of linear transformations. A key feature that we're going to be looking at today is that we are not necessarily going to be working with square matrices. So for example, let's consider the following change of coordinates system. We have variables x1 and x2 and variables y1, y2, and y3, and we have a linear relationship between them. y1, y2, and y3 are expressed as linear combinations of x1 and x2. Now this linear system can be rewritten in matrix form, in the ax equals y form, by taking the matrix of coefficients over here, the matrix 1, 2, 1, minus 1, 3, 4, which is a matrix with 3 rows and 2 columns. So we say it's a 3 by 2 matrix. Multiplying it by the vector x1, x2, and then equaling the right-hand side is the vector y1, y2, y3. So this is still an example of our fundamental problem of trying to invert a linear change of coordinates. The problem is still to try to solve for x1 and x2 in terms of y1, y2, and y3. But the fact that this matrix is not square now complicates the issue a little bit. What we really have here is a linear transformation. And the way we think about that is we think of starting with this vector, applying the matrix, so multiplying the vector x by this matrix, let's call it A, and that gives us the vector y. So we can think of this as an input-output situation where we're starting with a vector in two-dimensional space, which I might write A2 for affine two-dimensional plane. So there's our vector x right there. And this transformation t that we're defining this way takes the vector x and sends it to an element in three-dimensional space, in A3. That's this vector y right here. So the input is a vector x in two-dimensional space. The output is a vector y in three-dimensional space. Now we've looked at linear transformations already quite a lot. We've had a good look at 2 by 2 transformations earlier, like reflections, rotations, dilations. We've looked at 3 by 3 case also, transformations of three-dimensional space. This is now something a little bit different. It's a little bit more general because the space that we're starting with and the space that we're ending with are not the same spaces. They're different dimensions for one thing. So we cannot interpret this as a transformation of a space to itself. We have to interpret it in a different way as a transformation from one space to another space. So this is an example of a more general linear transformation in which the input space and the output space are not necessarily the same. Let's have a good look at it geometrically. There's the equation again, just to remind us. So t of x is this particular matrix times x, and we're calling that output y. And the vector x has 2 components, and the vector y has 3 components. So here's a picture of our two-dimensional input space, and here's a picture of our three-dimensional output space. Our input space has axes x1 and x2, and I remind you we're just in a general affine situation, so they don't have to be perpendicular axes, and they don't have to be equally spaced in the x and the y directions. We have some coordinate system. We have 2 basis vectors, E1 and E2, in this space. And over here in the y space, there's a direction y1, direction y2, direction y3, and various coordinates on those three axes. And our usual convention, I remind you, for three-dimensional space is that you should think of the y2, y3 plane as actually being in the board in that direction, and this y1 direction is sort of coming out at us. So it's a three-dimensional situation with y1 coming out at us. All right, so we want to understand what is this transformation doing. And a good place to start off with that understanding is to ask ourselves, what happens to the basis vectors under the transformation? So the vector e1, that's the vector with components 1, 0. So if we plug in the vector 1, 0 here and do that matrix multiplication, we're going to get 1 plus 0, 1 plus 0, 3 plus 0. In other words, the vector 1, 1, 3, which of course is just the first column of this matrix. And if we take the vector e2 with coordinates 0, 1 right there, then when we do the multiplication, 0 plus 2, 0 plus minus 1, 0 plus 4, we're going to get the vector 2 minus 1, 4, the second column vector. That's a familiar aspect of linear transformations, I hope, for you. You remember that when you apply a matrix to the basis vectors, the standard basis vectors, you're picking up the columns of that matrix. So let's give this vector a name, this first column. Let's call it v1. Let's call this v2. And these are two vectors in our three-dimensional space, so we need to picture them over here. The vector 1, 1, 3, okay, that would be 1 in that direction, 1 in that direction, 3 in that direction. So you could make a little box, 1, 1, 3. That's the vector v1. And the vector v2, it's 2 in this direction, minus 1 in this direction, so 1 over there, and 4 up. For a combination of 2 in this direction, minus 1, up 4. So there's the vector v2. So what do we know about this transformation is it sends e1, this vector here, to the vector v1 over here. And it sends e2, this vector here, to the vector v2 over here. So it takes this entire plane and maps it really onto the plane in three-dimensional space spanned by these two particular vectors. So every other vector in the space will be sent to a linear combination of v1 and v2. For example, the vector 1, 1 over here, which is e1 plus e2, will be sent to the vector v1 plus v2, which would be the vector in the same plane up in that direction. So the image of this transformation, the vectors over here, which are hit by something over in the input, that's a two-dimensional plane. And that's the name that we might use to describe that. That's the image of the transformation. Those vectors over here, which are the image of something from the input space. And that's a plane in our three-dimensional space. Now let's analyze the situation using row reduction. Let's think of this problem as simply a linear change of coordinates that we want to invert. So the augmented matrix for it would be our coordinate matrix on the left and our right-hand side y1, y2, and y3. So let's perform row reduction on this to see what solutions we get for x1 and x2. First thing we'll do is we'll use this top entry here, leading entry, to eliminate the two entries below it. So we'll take row 2 and subtract row 1. 1 minus 1 is 0. Minus 1 minus 2 is minus 3. y2 minus y1. And we'll take this row here and subtract 3 times row 1. 3 minus 3 is 0. 4 minus 6 is minus 2. y3 minus 3y1. Okay, now we've got something here. We would like that to be a 1. We could divide by minus 3 to make that a 1. So let's do that. So I've just copied it over here and I've divided this row by -3. So there's now a 1 there. That'll give us a bit of fractions here. So it'll be 1/3 y1 minus 1/3 y2 on the right-hand side. So we're going to take the third row and add 2 times the second row to it. So -2 plus 2 times 1, well, that's 0. Now we have to compute this thing, y3 minus 3y1, plus 2 times this. Okay, well, there'll still be a y3, minus 3y1 plus 2/3 of y1, that's minus 7/3 of y1. And 2 times this will be minus 2/3 of y2. That's the new entry there. It's now in row echelon form. To get it into a sort of fully reduced row echelon form, we could take this entry here, which is the leading entry, and use it to eliminate the 2 above it. Remember, the back substitution process, we're going up. Okay, so there we have a 1 there, a 1 there. There's only zeros in the rest of those columns. It's sort of in fully reduced row echelon form, except on the right-hand side, there's a little bit of ambiguity because we don't actually know what this element is. So this is also a leading entry if it's non-zero, because it's the first non-zero entry in that last row. And now it becomes actually quite crucial as to whether this quantity is 0 or not. Because if this quantity is non-zero, then this last row is impossible to satisfy, because it's saying 0 times x1 plus 0 times x2 equals this, whatever this is. If it's non-zero, that's impossible. So the only way our system has solutions is if this quantity is 0. And if this is 0, then we can read off what the solutions are. Then x1 will be this, because this first equation reads x1 plus 0x2 equals this. So x1 equals 1/3 y1 plus 2/3 y2. And the second equation allows us to read off x2. It's telling us x2 is 1/3 y1 minus 1/3 y2. But it only works if this quantity is 0, if 7y1 plus 2y2 minus 3y3 equals 0. So what does that mean? Well, that's exactly the equation of the plane that we called the image of t in the previous slide. Remember, in our three-dimensional space, there was a plane spanned by those 2 red vectors, v1 and v2. Well, the equation for that plane is exactly this one here. It's obtained from row reducing this augmented matrix. If this thing is 0, in other words, if a point lies in that plane, then we can find x1 and x2 that map onto it. Then, in other words, we can solve for x1 and x2 in the input space. And here are the values of x1 and x2. So this is how we invert the system, how we write x1 and x2 in terms of y1, y2, and y3, but it only works if this condition is satisfied. If this condition is not satisfied, it means that on the right-hand side of the previous slide, in that three-dimensional space, we have a vector which is not in the plane, not in the image. And so there's no way of finding a point in the input space that is sent to it. There's no solution. So this is an interesting, somewhat new feature, right? That the image of the linear transformation is given by, in this case, a plane, and that the equation of that plane is obtained from the row reduction of the original matrix. And if we want to, in fact, invert x1, x2 in terms of y1 and y2, well, the row reduction does it for us also. We've solved the system completely. All right, let's have a look at a second example now, which will, in some sense, sort of be reversed to the first example that we looked at. So we're going to be looking at a linear transformation now that's going from three-dimensional space to two-dimensional space. And there's our motivating change of coordinates. We have x1 minus x2 plus 3x3, we're told is y1, and 2x1 plus x2 minus x3 is y2. And we might be trying to solve x1, x2, and x3 in terms of y1 and y2. Trying to invert that linear system. We write down the system in matrix form as a matrix A times a vector x equals another vector y. The matrix A is just the matrix of coefficients here. The vector x has three components because there are three variables, x1, x2, and x3. The vector y on the right-hand side only has two components because there are only two equations. And now let's use the matrix A to define a linear transformation. This is our official definition of the procedure that goes from three-dimensional space to two-dimensional space. We'll call it S, as opposed to T in the previous question. So S of x is now defined to be A times x, where A is this matrix right here. And the output is y. And we're thinking of S as defining a transformation that inputs a vector x in three-dimensional space and outputs a vector y in two-dimensional space. And we want to do two things. We want to visualize what's happening here, and then we want to analyze it algebraically using, of course, row reduction. All right, so first let's have a look at the geometry of it. There's our transformation. S of x equals this matrix, a 2 by 3 matrix, times this vector x, which has three components, x1, x2, x3, and that's equal to y, the vector, with two components, y1 and y2. And we're going now from a three-dimensional space, the x space, to the two-dimensional space involving y's. So here's our three-dimensional space as usual, the x1 axis coming out at us, the x2 axis in the plane of the board, the x3 axis in the plane of the board. And some coherent coordinates on each of the axes. So we're thinking now of taking a vector in this space and applying S to it. We're going to end up with a vector over here, which is just the usual two-dimensional space with a y1 coordinate in that direction, y2 coordinate in that direction. So how are we going to analyze this? The simplest thing to do is to ask what happens to the simplest vectors. Which are the standard basis vectors? The vector e1, which is 1 unit in the x1 direction, e2, 1 unit in the x2 direction, and e3, 1 unit in the x3 direction. So to find out what happens to e1, S of e1, we just take this matrix and we apply to it, multiply it by the vector 1, 0, 0, which is the name for e1. In this coordinate system, it's the vector 1, 0, 0. And when you multiply by 1, 0, 0, you're just picking up that first column, which we'll call v1. When you apply the transformation to e2, you're multiplying by 0, 1, 0. That's the second basis vector. You're picking up the second column, minus 1, 1. We'll call that v2. And S of the third basis vector, that's 0, 0, 1, gives the third column, 3, minus 1, which we'll call v3. And these three vectors, v1, v2, and v3, are over here on this part of the picture. There's v1, the vector 1, 2, v2, the vector minus 1, 1, and v3, the vector 3, minus 1. So this linear transformation takes the first basis vector and sends it to v1. Imagine that's sent to there. And the second basis vector e2, that's sent to that vector there. And the third basis vector e3 is sent to v3. And the rest of the space is completely determined by that information because it's a linear transformation. So for example, if we wanted to know what would happen to the vector, say, 2, 1, 5. Where's the vector 2, 1, 5? 2, 1, 5. Where's that vector going to go? The answer is it's going to go to the combination 2 times v1 plus 1 times v2, I suppose that would be like that, plus, what did we say, 5 times v3. So it would go to that vector there. So linearity forces or determines where any other vector is going to go once we know where those 3 basis vectors go. And I guess it's pretty obvious then that the image of this transformation is the entire plane over here. Every vector over here is some combination of these 3 vectors. So any combination like that can be hit by some appropriate vector over here. You might be a little bit disappointed by that because in the last example we had this rather interesting subspace over on the right hand side. And here it's not so interesting, we're just getting the entire plane. But to make up for that, there's something that's interesting that's happening over on this side of the space that we didn't see in the previous example. It's a new idea, and it's the answer to the question, which vectors under the transformation are sent to the 0 vector? We have 3 dimensions over here, and we're mapping onto 2 dimensions. Intuitively, we think, well, maybe a couple of vectors are actually getting sent to the 0 vector, not just one. Of course, the 0 vector always gets sent to 0. But it turns out that this particular vector, the vector -2, 7, 3, gets sent to the 0 vector. Let's just check that. If we take this matrix and multiply by -2, 7, 3, what would we get? We get -2, -7, plus 9. That would be the first entry, that's 0. The second entry would be -4, plus 7, -3. That's also 0. So this vector, which is somewhere along this line, is sent to 0. And in fact, any multiple of it is also sent to 0. Because it's a linear transformation. So any vector on this green line is sent to 0. That means this is a special subspace of our initial space. Just like in the previous example, the image was a special subspace of the right-hand side for that linear transformation T. Let's now see how we could find these things out purely algebraically. All right, so let's analyze that AX equals Y equation. There's the matrix A. Our unknown vector X corresponds to columns X1, X2, and X3. And the right-hand side of the equation, Y1, Y2, that column right there. So let's row reduce this augmented matrix for the system to try to solve the system, to try to find what X1, X2, and X3 are in terms of Y1 and Y2. We'll use that 1 as a leading entry to eliminate the 2 below it. So we'll take row 2 and subtract 2 times row 1. 2 minus 2 is 0. 1 minus 2 times minus 1 is plus 3. Minus 1 minus 2 times 3 is minus 7. And y2 minus 2 times y1 is just y2 minus 2 times y1. Okay, now we're going to multiply this row by 1/3 to make that leading entry a 1. So we've divided by 1/3. And now we're going to use that leading entry. We're going to go back substituting now to use that to eliminate the entry above it. We're just going to add this row to the first row, giving us 1, 0. We add this to that, we get 2/3, and add this to that, we get 1/3 of y1 plus 1/3 y2. It's already in fully reduced row echelon form because there are the 2 leading entries. They are both 1, and the columns containing them are all just zeros. So we can read off the solutions. And the solutions have a parameter involved because on the left-hand side, these 2 leading columns are not the only columns. There's also a non-leading column, that one right there. That non-leading column corresponds to a parameter. So the third variable, x3, we'll set that equal to a parameter lambda. And then we can solve for x1 and for x2. Now, to make life a little bit easier, let's just have a look at the special case when y1 and y2 is the 0 vector. When y1 and y2 are both 0, so that what's on the right-hand side is 0, 0. In that case, the solution reads x1 equals minus 2/3 lambda, and x2 equals 7/3 lambda. So the solution to that system, ax equals 0, is the vector x has to be some multiple of minus 2/3, 7/3, 1. And by scaling, multiplying by 3, we can get rid of the fractions there. Just make it minus 2, 7, and 3. And that's where that vector came in. Remember I said that this vector here in the input space is a distinguished direction, that if you walk in this direction and apply the linear transformation, you always get the 0 vector. So the system ax equals 0 has as its solution just all the multiples of this vector here. Now, another important application of row reduction in linear algebra is to help us understand two concepts called the concept of a spanning set and the concept of a linearly independent set of vectors. So those are the two concepts that we're going to have a little look at now. I want to restrict ourselves to the three-dimensional situation, which is pleasant because we can visualize things. But pretty well everything that I'm going to say works in 2 dimensions, in 4 dimensions, in 5 dimensions, and so on. And we'll talk about that a little bit later. It's good to start with 3-dimensional space, 2-dimensional space to solidify our intuition. So, what's a spanning set? Well, we're going to work in 3-dimensional space. And we'll say that a set of vectors, say v1, v2, up to vn, a set, is a spanning set for 3-dimensional space precisely when every vector in the 3-dimensional space can be written as a linear combination of those n vectors v1 through vn. This is a linear combination, right? It's some multiple of v1, a1 times v1, where a1 is some number, plus some multiple of v2, say a2 v2, and so on all the way up to some multiple of vn. So we can take some multiple of those vectors and get any old vector, then this is a spanning set. Let's look at some examples. First example. It's the most important example because this is your typical best spanning set. The vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. You recognize the 3 basis vectors, the vectors which are just one component in each of the 3 coordinate directions. The claim is that is a spanning set. And that's almost obvious because any vector can be written as a linear combination of those 3 in a very obvious way. So for example, suppose that you're given the vector 4, 5, minus 2. How are you going to write that as a linear combination of these 3? You're just going to take 4 times the first basis vector plus 5 times the second basis vector plus minus 2 times the third basis vector. It's pretty obvious that doesn't work just for this vector. It works for any vector here. It doesn't matter what 3 entries they were. We can always write any vector as a linear combination of those 3 vectors. So this is a spanning set. There's one additional thing to say about this situation is that in this case, there's in fact only one way of writing this vector as a linear combination. We didn't have any choice at all. This number had to be a 4 because the top entry has got to match with the 4 there. This entry has to be a 5 because the second entry has to match with that 5. And this entry has to be minus 2 because the third entries have to agree. So this linear combination is in fact unique. There's only one way of writing this vector as a linear combination of those three vectors. That's not part of the definition of spanning set. That's an extra aspect of this particular spanning set. So a few more examples. Second example, consider these four vectors in three-dimensional space. The three basis vectors together with the vector 2, 1, minus 5. That's also a spanning set. For example, the vector 3, 1, 4 can be written as 3 times this vector, plus 1 times this vector, plus 4 times this vector, plus 0 times that vector. We're just basically using the idea from the previous example and disregarding this vector by giving it coefficient 0. So this vector can certainly be written as a linear combination of those, and pretty obviously any vector can be written in the same way as a linear combination of those four vectors, just by ignoring this one and applying the argument of the previous example. However, this vector here can also be written in another way. It could be written as 1 times this vector plus, and then we'll add 1 times this vector to give a total of 3. And then the middle entry is 1, that's okay. And the bottom entry is 4, so we'll add 9 times this vector. Right? So that's another way of writing this particular vector as a linear combination of the four vectors. Actually, the other vector has 0 coefficient, so I'm not writing it. Which shows us that, in general, the linear combination is not unique. It's different from what it was last time. And it's because we have, in some sense, too many vectors. There's a bit of redundancy. We have some extra freedom because we have so many vectors at our disposal to make combinations with. So it's still a spanning set, but now the linear combinations used are not unique. How about these four vectors in three-dimensional space? 1, 0, 0, 0, 1, 0, 2, 5, 0, 3, minus 1, 0. Well, a little bit of thought shows that this is not going to be a spanning set. Even though there are four vectors, these four vectors do not span three-dimensional space because this particular vector is not a linear combination. And how can we see that? Well, it's because this vector has a third component, which is 1, and all of these vectors have 0 in their third component. So no matter what combination we take of those three vectors, we'll always have 0 in the bottom component, so there's no way a linear combination of these four can make this vector. And if you can't make just one vector, it means that it's not a spanning set. This set is not a spanning set. All of these examples are pretty easy because the vectors I've chosen are relatively simple. However, for a more general situation, it's not at all so easy to tell whether a given set is or is not a spanning set. And that's where row reduction comes in to help us. Right, so how in general do you tell if you have a spanning set? The answer is we row reduce. So, for example, someone gives us the set S with three vectors. First one, 1, 2, minus 1. Second one, 2, 0, 1. The third one, minus 1, 4, 3. We want to know, is that a spanning set for three-dimensional space? We have these three vectors. Geometrically, what we're asking is, are these three vectors kind of in general position? Or are they perhaps all lined up to be in a plane? If they're all in a plane, then they're not going to be a spanning set because any multiple is also going to be in that plane. But if they're kind of in random general position, then yes, you'll be able to write any vector as a linear combination. But we're not sure until we've done the algebra. This is a system that we're interested in because we're trying to ask, given a general vector, say y1, y2, y3, can we write a general vector as a linear combination of these three vectors? In other words, can we solve the system y1, y2, y3 equals a1 times this vector plus a2 times this vector plus a3 times that vector? We want to know, is there always a solution? No matter what y1, y2, and y3 are. Well, that's a linear system, in the unknowns A1, A2, and A3. The coefficients are now the unknowns. We want to know, is there always a solution? Well, we write down the augmented matrix. The augmented matrix is this one here, where this matrix on the left-hand side is just these three column vectors put together. Because the first equation, for example, is A1 times 1 plus A2 times 2 plus A3 times minus 1 equals Y1. So the coordinates are 1, 2, minus 1, Y1 on the right. So this is the matrix that we have to row reduce, and we want to know, is there always a solution? Well, it's going to turn out that it doesn't matter what Y1, Y2, and Y3 are. We're not going to have to carry on following through with the right-hand side. So I'm going to be lazy, and I'm just not going to evaluate the right-hand side. I'm just going to put stars there. Okay? Something's happening there, but we're going to see that it doesn't matter what's happening. It's what's happening on the left-hand side that's all important. So we're going to row reduce the left-hand side. So we'll start with this entry and subtract multiples of this row from these rows to make this entry 0 and this entry 0, and we get that. Okay, now what we can do, we'd like to make this entry here 1. Well, one way of doing that is to divide by 4, or minus 4. Another way of doing it, which is maybe a little bit clever, is to just simply add this third row to it. That'll put a minus 1 there, and it'll make that an 8. We'll do something to that. Well, then I'll just multiply by minus 1. So I'm going to multiply by minus 1, so I get 1 minus 8 and something. So I've done two little steps there together. I've added the third row to the second row and multiplied the second row by minus 1 purely because of laziness, because I wanted to get a 1 there so I don't have to deal with fractions. It's not compulsory, just makes it a little bit easier. Now the next thing we have to do, use that 1 to get rid of the 3. It's pretty easy. I'm just going to take that third row, subtract 3 times that second row, giving us 0, 0. 2 minus 3 times 8 is 26. And again, there's something on the right-hand side. It's in row echelon form already, but we can put it into fully reduced row echelon form pretty easily. We'll divide this equation by 26. There it is right there. And then we'll take this equation and this row, and we'll add 8 times it to this and 1 times it to that. So those will become zeros. And then the next step, we're going to add this row, or add minus 2 times this row to this one to make that 0. And what's happening on the right-hand side is changing in some fashion. We don't know what it is. But at the end, where it's clear, we're going to get just the identity matrix on the left-hand side. 1, 0, 0, 0, 1, 0, 0, 0, 1, and something on the right-hand side. Now, what were we interested in? We wanted to know, does the original system always have a solution, independent of the right-hand side's particular values? And we can see right here that it does. There's a unique solution. The unique solution is A1 equals whatever this is, A2 equals whatever this is, and A3 equals whatever this is. There's in fact a unique solution because there are no parameters. There are no non-leading columns on the left-hand side. We have 3 leading columns. So the answer to our original question is yes, this is a spanning set, because we can always solve this system to find A1, A2, and A3. In fact, we always get a unique solution. All right, so let's have a look at another example. We have now 4 vectors in this set. 4 vectors in 3-dimensional space, making the set P. We want to know, is P a spanning set? That amounts to the question, can we always find a solution to this vector equation? No matter what y1, y2, and y3 are, can we always find a1, a2, and a3, and a4 so that this system has a solution? In other words, that we can write this vector as a linear combination of those 4. Well, that's a system of 3 equations in 4 variables. The variables are A1, A2, A3, A4. And there's one equation essentially for each entry of those vectors. Here's the augmented system. We don't need to go any further. It's already in row echelon form. It's not in fully reduced row echelon form because we haven't gotten rid of that 0, but there's no need to do. We're only interested in the question, does this system always have a solution or not? And the answer is, it does not always have a solution. Because the entry that's here, well, it depends on what the y1, y2, and y3 were. This is going to be some linear combination of y1, y2, and y3, like maybe 3y1 minus 2y2 plus 5y3, or something like that. But it's potentially non-zero. And if that's non-zero, then that row there, which has this entry as a leading entry, is a row that cannot have a solution. So the fact that this is a leading column, or potentially a leading column, means that this does not always have a solution. And so, the original set of vectors is not a spanning set. Now let's have a few examples of spanning sets in simpler two-dimensional space. What does it look like there? Here's a two-dimensional affine space with coordinate axes x1 and x2. And here's 3 particular vectors. There's v1, there's v2, and there's v3, which just happens to be in the same direction as v1, but in the negative direction. All right, well, first of all, the set v1, v2. Set this vector plus this vector. That is a spanning set, geometrically, because any old vector could be written as some combination of this one plus some combination of v2. You can see that geometrically. However, v1, v3, that set consisting of this vector and this vector, that's not going to be a spanning set, because any combination of these two vectors is still going to be in this direction. Right? If we take 2 times this vector v1 and 3 times vector v3, we're still going to end up with a vector that's in this line. So you can't get every vector just from these two. This is not a spanning set. While v2 and v3, that is a spanning set. And if we put all 3 of them together, it's still a spanning set because just v2, v3 say is a spanning set. So adding vectors to a spanning set still keeps it a spanning set. Now there's another notion that's complementary to the notion of a spanning set. Sort of the opposite side of the balance to it. Spanning set on the one hand, linearly independent set of vectors on the other hand. So that's a little bit trickier concept in some sense. Some students find it a little bit harder to appreciate. And however, row reduction is still going to be the crucial thing to decide when a set is linearly independent. Let's have a look at that concept now. So we'll still work in 3-dimensional space. And we'll say that a set of vectors, v1, v2 up to vn, is linearly independent precisely when none of the vectors can be written as a linear combination of the others. So if none of the vectors can be written as a linear combination of the others, then it's a linearly independent set. Now, maybe that's a little bit of a mouthful. Let's see what it looks like in practice. Here are 3 vectors, very familiar vectors, just the 3 basis vectors in 3-dimensional space. It's a linearly independent set because, well, you can't write this one as a linear combination of those 2. You can't write this one as a linear combination of those 2. You can't write this one as a linear combination of those 2. How about this example? Here we have the vector 1, 0, 0, 0, 1, 0, and 2, 3, 0. Well, this is not a linearly independent set because this vector here can be written as a linear combination of those 2. It can be written as 2 times this one plus 3 times this one. Actually, a little bit of thought shows that you could actually change this around. Once you realize this, you could also say, but wait a minute, the vector 1, 0, 0 could be written in terms of these two. How? We could write this one as, so divide by 2, so it'd be half of this one minus 3 halves of this one. So this kind of combination is not unique. What do we say when the set is not linearly independent? We say that it's linearly dependent. So linearly dependent means that one of the vectors, at least, can be written as a linear combination of the others. The next example may strike you as a little bit perverse. It's a set with 3 vectors, one of which is the 0 vector. There's nothing preventing the 0 vector from being part of this discussion. So is this set linearly independent? Well, no, it's not. It's in fact linearly dependent because the 0 vector can be written as a linear combination of these two. In the most trivial way, it's simply 0 times this vector plus 0 times this vector. Does that count as a linear combination? Yes, it does. So this vector is a linear combination of those two. This is not linearly independent. So it's linearly dependent. And so generalizing that, if you have any set containing the 0 vector, then that's going to be a linearly dependent set. Unless you just have the 0 vector all by itself. Here is another example. We've got 3 vectors, 2, 3, minus 1, 4, 2, 1, minus 2, 5, minus 5. And the claim is that this is a linearly dependent set. Why? Because minus 2, 5, minus 5 happens to be 3 times this vector minus 2 times this vector. Geometrically, it means that these 3 vectors lie in a plane, because if there's the vector 2, 3, minus 1, there's vector 4, 2, 1, then this vector is some linear combination of them. So all 3 vectors lie in a plane. But how do we come up with this equation? Given a set of vectors which are rather general, how do you determine methodically, straightforward algorithm, whether or not the set is linearly independent? Again, it's reducing to a system of linear equations. Ultimately, it comes down to row reduction. Let's have a look at an example. Here are 3 vectors, v1, v2, and v3, and we're interested in the question, is this set of vectors linearly independent? So, can we write v1 as a linear combination of v2 and v3, or v2 as a combination of v1 and v3, or v3 as a combination of v1 and v2? Well, instead of looking at all those 3 possibilities separately, we can combine them all into one equation. Any one of these equations can be rearranged by bringing all the terms to one side and leaving just the 0 vector on the right-hand side. So if any one of these is true, that means that we can write an equation like this where at least one of these coefficients, alpha 1, alpha 2, and alpha 3, is non-zero. So linearly independent means that we can't write this. It means we can't find a relationship like this where at least one of them is non-zero. Or in other words, the only solution to this is the trivial solution alpha 1 equals alpha 2 equals alpha 3 equals 0. So that's the condition of linearly independence. The set is linearly independent precisely when this equation has only the trivial solution. And that's an equation that we can tackle using row reduction. So let's have a look at how it looks like in this particular case. So here's the matrix form for that equation. Here's the vector v1, vector v2, the vector v3. When we multiply by alpha 1, alpha 2, alpha 3, what we're doing is we're taking alpha 1 times the first vector, plus alpha 2 times the second vector, plus alpha 3 times the third vector. And we're setting that equal to 0. and asking, is there a non-zero solution to that equation? There's always the zero solution. So alpha 1, alpha 2, alpha 3 equals 0, 0, 0. That's always the solution. We're interested in, is there any other solution? The augmented matrix is this one. And since there's only zeros on the right-hand side, when we row reduce, those zeros are going to remain. So it's unnecessary for us to copy those zeros down when we row reduce the matrix. We'll just row reduce the left-hand side. And there it is there, and I've row reduced it for you. You can check it until we've gotten to this row echelon form. At this point, we can see that all the columns are leading columns. And that means that there's a unique solution to the system. If all the columns on the left-hand side are leading columns, then there's a unique solution, namely the solution that we already know exists, alpha 1 equals alpha 2 equals alpha 3 equals 0. And that tells us that the original set is indeed linearly independent. We have 4 vectors this time, still in 3-dimensional space. And the question is this set of 4 vectors linearly independent? Again, it amounts to this equation here. We're looking at this equation, some linear combination of the 4 vectors equaling the 0 vector. And we want to know, is there a non-zero solution to this equation? If there is, the set is not linearly independent. If there's only the 0 solution, then the set is linearly independent. There's the matrix form for this equation. The columns are just the vectors that we started with. Over here we have a multiplication by a vector with 4 components, something a little bit new, representing the fact that there's 4 terms in this sum. So the top line, for example, would be alpha 1 times 1 plus alpha 2 times 2 plus alpha 3 times minus 4 plus alpha 4 times 3 equals 0. There's the augmented matrix. And we can row reduce that just like we usually do to find all possible solutions, alpha 1, alpha 2, alpha 3, and alpha 4. Each one of those variables corresponding to one of the columns of this augmented matrix. And as before, since there's a right-hand column here of zeros, we can ignore that when we do our row reduction because that always stays zeros. So there's the original matrix on the left-hand side. Row reduced it in the usual way. So I'm going to use this entry to eliminate the minus 1 below it, giving us that. And then we're going to use this 1 to eliminate the 5 below it, giving us that. At this stage it's in row echelon form because the leading columns are staggered down to the right. The associated augmented matrix to the system here is just what we get by copying that over here and putting zeros back where they were before. And we can see that now there are 3 leading columns on the left-hand side and 1 non-leading column. This non-leading column corresponds to a 1-parameter family of solutions. When we write down the solutions, which we don't have to do because we're not interested in what the solutions exactly are, but if we wrote them down, then the 4th variable would correspond to a parameter. There's a parameter of solutions. There's more than just the trivial solution. So the original set is not linearly independent, or it is linearly dependent. All right, so we've accomplished a lot in this lecture. Now some exercises for you to practice the ideas. Our first exercise, solve for the x variables in terms of the y variables. 4 different situations. And I warn you that whether or not there are solutions, whether or not you are able to solve for the xi's in terms of the yj's, might very well depend on the yj's. So there might be a condition on the yj's that you need to look at. Our second exercise, find all solutions to these 2 equations in the variables x1, x2, and x3. The notable thing being that the right-hand side is 0. And our third exercise, describe geometrically the following linear transformations. So I'm giving you the transformation in terms of t of x equals this matrix multiplying some unknown vector x. And part of the question is to figure out how big that vector x is. I can tell you, say for the first one, the vector x has got to have two components, because that's the only way that you could multiply this matrix by the vector. So the vector x here will have components x1, x2. And so it's inputting a vector with two components and outputting a vector with three components. So I want you to describe what that transformation from two-dimensional space to three-dimensional space looks like geometrically. And same for these ones here. In our fourth exercise, I'm asking you to find out which of these are spanning sets of three-dimensional space. And the fifth question, explain why every spanning set of either two-dimensional space or three-dimensional space must have at least two, respectively, three elements. So a spanning set of A2 has at least two elements. A spanning set of A3 must have at least three elements. And our final two questions have to do with linearly independent sets. In the first one, I'm asking you to figure out which of these sets is linearly independent. And the last question, explain why every linearly independent set in two-dimensional space must have at most two elements, and why in three-dimensional space it must have at most three elements. So that's a fair amount of work for you to do. And next time we are going to move up a little bit of a step, going from 2 and 3 dimensions to higher dimensions also. We're going to consider general linear transformations. And we're going to be especially interested in two important ideas: the rank of a linear transformation and the nullity of a linear transformation. So I hope you'll join me for that. I'm Wildberger. Thanks for listening.